Hi there. Welcome to the course. Today we've got a couple different things to talk about. Let's just kind of lay out our agenda. Today's agenda. What we're going to focus on is the following couple things. First, we'll provide a little bit of motivating information as to what control actually is. So, what is control? Okay, so we'll talk about this for a little while. We'll do some intuitive examples, that sort of thing. Okay, after that, what we're going to do is we're going to give a very formal definition for what a system actually is. Okay, so in this course, we're going to be talking a lot about systems theory, so it's important that we actually have some sort of clear idea of what a system actually is. Okay, all right, once we've done that, we're going to take some time to talk about representations of systems. Okay, so this is our rough agenda for today. Okay, great. So let's start with the first point. What is control? Okay. So for some of you, this might be kind of your first course in control, right? Maybe you saw it was interesting in the course catalog and you decided to pick it up. What we're going to do here is we're going to kind of get a rough feel for what control actually is with a very kind of basic example. Okay? So let's consider an example of a shower system. All right, shower system. Very exciting. Okay, so let me sketch out what the shower might look like. Let's say we have some shower head over here. It's dispensing some water out like this. And we got a couple different things in the system. One of them is we have a shower handle over here. Okay, so I could turn the shower handle and I can kind of control the temperature of the water as a result. Okay, so this is my water coming out. This is my shower handle. What else have I got? Well, let's say, I want to kind of measure what the temperature of this water is. And to do that, I'll stick my hand into this water, right? And I'll get a feel for what the temperature is. Okay. So how is this a control system? Here's what we're going to do. What we're going to do is we're essentially trying to control the state of this shower system. Okay? So we have a goal in mind, which is to control the temperature of the water. All right? So what I'm going to do is I'm going to stick my hand into the shower water. I'm going to see if it's a temperature I like. If it's a temperature I like, great, I'm done, right? I'll just kind of keep it there. If it's a temperature I don't like, I'll adjust the position of the handle. I'll stick my hand in again. I'll take a new measurement, and so on and so forth. Okay? So the basic idea is I take a measurement, I take an action according to that measurement, and I repeat. Okay? So what's going to happen is if I kind of iteratively continue this process, right? Take measurement, correct the shower handle position, take another measurement, correct handle position, and so on, I'm eventually going to converge to my desired shower temperature. Okay? So converge to the desired temperature. All right, fantastic. So this is one basic idea of control. Okay? What we're doing here is we're using feedback about the current state of our environment, which we kind of measure by sticking our hand into this water, to kind of control the state of the environment, right? So we're using what measurement we have of the shower water temperature to take some sort of action as to how we should change this water temperature, right? So this is the key idea one. So of control, what we kind of do is we take measurements of our environment and take actions that depend on those measurements. Okay, so there's a couple different things at play here. One of them is that we're kind of continually doing this process of measuring and taking actions, right? Why is this? Why don't we just take one measurement, kind of be like, okay, that's where the shower handle was yesterday. Maybe that's fine, right? Why don't we just do that? So the idea is, key idea 2 is by continually measuring and adjusting, we can become robust. All right? So let's say, maybe something happens to our system that we weren't expecting, right? Let's say, I don't know, your roommate turns on the dishwasher or your roommate jumps in the shower, like next door or something like that, right? That's going to have some sort of unanticipated effect on the behavior of our shower system. And maybe the handle position that worked well for us yesterday is no longer a good one, okay? So by continually doing this process of measuring and adjusting our actions according to new measurements, we can get a feel for what our system is doing at any given time, and we can make the best decision given current measurements of our system, okay? So we say that our system is going to be robust to uncertainty or robust to disturbances if we kind of do things in this manner. All right, fantastic. So these are really the two core ideas of control theory that we're going to focus on in this course, all right? First, let's ignore any uncertainty and just say, I want to control the state of the system to be this temperature, okay? So that's kind of what key idea 1 is. We want to use measurements to drive our system to a desired state. Key idea 2 is, if our system has uncertainty, we can use feedback to overcome that uncertainty. Okay, fantastic. So here's what we're going to do now. What we want is a precise mathematical theory of systems and control. Okay? So this is kind of where we're headed in this course. This is a course on linear systems theory, right? So it makes sense that we want a very precise mathematical, theoretical framework for control. Now, what's our kind of first step in this process? Well, something that kind of makes sense, but maybe is something that you haven't thought about before, is we want or need a precise definition of a system. Okay? So maybe this is something you haven't thought about before, but how do we actually define a system, right? What is a system in a precise mathematical sense? Okay? So this is really the question that we're going to focus on in today's lecture. We're going to figure out how we can really precisely reason about what systems are, what properties they have. Okay. So here's what we're going to do. So our plan for the next foreseeable couple of minutes is we're going to use the shower example as a template for a formal definition. Okay, so what we're going to do is we're going to kind of take a look at all the different key parts of the shower example and really distill out the essential features that are at play that really kind of make it work as a control system. Okay, so let's start out by asking, what are the basic objects? Basic objects in the shower control system. All right, so kind of just take a minute and see if you could reason about this a little bit. Okay, so I'll assume that you've taken some time to kind of think about what this is. Let's kind of discuss the different key objects at work here. Now, I want to emphasize we're going to start at a really, really basic fundamental level, okay? So some of the things I write will seem a little bit obvious, but, bear with me. We're kind of trying to feel out a precise definition here. Okay, so one of the things that we have is some notion of time, right? So we know the time of day at which we enter the shower, and the current time of day, right? So what we could do is we can maybe represent the time of day with some sort of real number, right? So let's say time is a real number, little t belonging to r. Okay, good. So that's our first object. What else we got? Well, in the examples above, we were using the shower handle to kind of, control the state of the system, right? So in control, this is something that we refer to as an input to the system. So our second object that we have is an input, right? So what we do is we interact with the shower system via the position or angle of the shower handle, right? So what we have is that input values might be an angle, right? So let's call it an angle theta in r, okay? So note that I'm being pretty simplistic about what these spaces look like, right? Obviously, the shower handle position can't take on every real number, right? But, this is just a simple example, so kind of bear with me as I make some simplifying assumptions here. Okay, so let's say our input values are some values in the real numbers, okay? What would our input signals be? Well, input signals are then maps from time to input values. Right, so instead of just specifying, one single value of our input, a signal kind of specifies all the different values of inputs across time, okay? So we could maybe write an input signal as a function going from r, which represents time, into also r, but this r represents kind of the handle position, okay? Okay, very cool. So let's move on to discuss outputs. All right, so this is kind of the next key component of our system. What are the different outputs of the system? Well, I just want to make a quick clarifying point. What we mean by outputs in the context of control is generally measurements that we're taking of our system, okay? So output is really just a fancy word for measurement. This is also sometimes used for what quantity in the system you'd like to control. Oftentimes that coincides with something that you're measuring, okay? All right, so the outputs, aka measurements of the system, are the temperatures we take with our hand, right? So I go ahead, I stick my hand into this water and I say, okay, this is the current water temperature. All right. So I don't know about you, but my hand is not a thermometer, right? There's really only a couple different temperature measurements that my hand can understand, right? So let's say measurement values belong to the set. Maybe let's say icy, cold, mild, hot, and ouch. Let me underline that in red because it's super hot. All right. So these are the different measurement values that my hand can feel when I put it into the water, right? I'm going to kind of get one of these things back every time I take a measurement. So these are my measurement values, right? Now my measurement signals are maps from time, t and r, to the set of measurement values, okay? So again, we have this, kind of duality appearing. We have values, which are, particular values, either of an input or an output or some such thing, and signals, which are actually maps from time to those particular values, okay? So this is an important distinction to make, and it's one we'll talk about formally a little bit later. All right, so we've covered time, input, output. What else do we have in this system? Well, we know that icy, cold, mild, hot, and ouch don't actually represent what's really going on in our system, right? Those aren't true kind of measurements of our shower temperature, all right? So underneath these different output values, what we have is the true temperature of the system, all right? And we'll refer to the true temperature of the system as the state. All right. So the state is the true temperature of the water. Okay? And I'll use a capital letter T and R to denote water temperature. Okay. So what properties should this state satisfy? Well, if we assume a very, very simple model of our shower, then knowing the current temperature, current time, start time, and input signals should kind of give us some idea of what the system's going to do next. Okay? So it should tell us what the system does next. All right? So there's some notion that this state is kind of encapsulating everything we currently know about the system, right? If I know my state and I know what my input is, I should know what the system will do next. Okay. So these are really the four fundamental objects in our system, right? Now, how are these things tied together, right? How are objects 1 to 4 related? Well, there's a couple of different maps that kind of relate these things that really exist implicitly in this model of a shower system, right? And there are two different maps. So map 1, we have something called the state transition map. All right, so it's a kind of fancy name. What does this mean? Well, we know that underlying this shower system, we have some map that tells us the relationship between your start temperature times and times inputs and current temperature. Okay? So what the state transition map is it's a map that kind of tells us how the system temperature, right, the true temperature, will evolve depending on the passage of time and the inputs. Okay? So this really describes everything about the motion of the system. Okay. So what else do we have? Well, the state transition map is giving us a model for how kind of the internal true state of our system is evolving, right? Now, what we also had in this example above, where I went ahead and I stuck my hand into this water, was some model underlying how measurements are being taken in the system, right? So we could also really represent this as a map. So 2, what we have is something called the readout map. What the readout map does is it is a map describing the measurement process. Okay, so let's say it takes in a current time, a true temperature, and handle position, and returns the measured temperature, right? That temperature from that set, icy, cold, mild, hot, ouch, that my hand actually feels, right? So it returns the measurement temperature. Okay, so, I just kind of want to discuss real quick why it might need to depend on all these different quantities and not just the true temperature, okay? So current time, maybe if I've been sitting in the shower for a while, I kind of got used to the water temperature, right? So my hand isn't feeling as hot anymore. And handle position, if I'm looking at the handle position and I see it's, cranked all the way up, I don't know, maybe there's some sort of placebo effect. And I think, okay, this is a little bit hotter than it actually is. Okay? So what we do is we use the readout map to describe how measurement processes are being kind of formed, underlying this very intuitive shower example. Okay. So, what was kind of the point of all of this? Well, what I want to do is I want to use this example as a template for a very abstract definition of a dynamical system. An abstract definition of a system. Okay? So what I'm going to do next is I'm going to define a very abstract mathematical definition for a dynamical system, and I'm going to do this in a manner that kind of reflects all these different objects that we just laid out over here. Okay? So as I'm going along and writing this definition out, just kind of take some time to see if you could recognize the different elements of the shower example and how they kind of abstractify in this, fancy new mathematical definition. Okay, so that said, let me write this definition out. So definition, this is a causal I/O dynamical system. Just as a brief side note, I'll often abbreviate dynamical system as DynSys. Okay? So I hope it should be a little bit clear from context what I actually mean by this. All right, let's go ahead and state the definition. So here's what we have. Let a set T subset R, I'll use this curly mathcal T, if you're familiar with LaTeX, to denote this T. Let curly T subset R be a non-empty set. What we say is a causal I/O dynamical system on the set T is a tuple or ordered set D, which contains the following information. It contains a set U, a set Y, a set sigma, a map phi, and a map R, and all of this data needs to satisfy the following. Okay? So first, what we have is T is called a time set. All right? So what the set T is the set of all possible times in the system. Okay, so for the simple example of the shower, this was something like the time of day, right? Maybe we were measuring it in seconds or minutes or some such thing, but it's all the different possible times of the system. Okay. Now, what do these other different components represent? Well, two, we have the input space. All right, so we say that this set curly U over here, or mathcal U, whatever you'd like to call it, is the input space of the system. Okay, so U is the input space. And what this is a set, which is a subset of all possible mappings, little u, from your time set T to some fixed set of input values, okay? Where U is called the input value space. All right, so what the input space is a set of possible input signals, okay? It's not a set of possible input values, but a set of possible input signals, all right? So what this means is that every element of the input space is actually a function. It is not a value, all right? So what we require is that functions in curly U take on values in non-curly U, okay? So input signals in the input space take on values in the input value space. All right? So let me just emphasize this. This is a set of signals. All right? So just to kind of clarify this point a little bit more, in the case of the shower example, the input space would have been the set of all input signals corresponding to how I was turning the handle of the shower over time. Okay? Now, on the other hand, the input values in that case would have been the actual possible angles of the shower handle. All right? So each input value was a real number. Each input signal was a map from time to the real numbers. All right. So that's the input space. Now, next up, what we have is the output space. All right. So this set Y, which is up next, is the output space. And this is defined very, very similarly to the input space. All right? So we define it to be a set Y, which is a subset of the set of all mappings, little y, from your time set t to some fixed set, non-curly y. All right? Where this non-curly y is called the output value space. All right? So once again, the actual output space itself is a set of signals, right? Not a space of values, right? If one wishes to really emphasize this point, you could call these spaces the input signal space and the output signal space, all right? And this is what these things really are. Now we have this set non-curly y called the output value space, all right? So what an element of the output space is a mapping from time into the output value space. Okay. What else do we have? Well, next we have a set called sigma. And what sigma is the state space. All right? So as opposed to being a set of signals, state space is just a regular set. All right? So what we have is that sigma is the set of possible states of the system. Okay? So remember from the shower example, this state was kind of something that really summarized the next possible behavior of the system, right? If we had the state, the current time, and the current input, we could kind of figure out what the system was going to do next. All right? So this really summarizes everything that's currently going on inside this system. Okay. So we've outlined these four fundamental objects, right? These are essentially the same objects that we had in the shower example, right? Just said in much more abstract language. All right. So what we did next, after defining these four objects, was we defined the state transition map and the readout map, right? Both of these represented some sort of fundamental process underlying the abstract system, right? The state transition map described how the true temperature of the system would change, while the readout map described how our measurement process was occurring. Okay. So let's describe how these kind of show up in the abstract setting, what they look like. All right. So 5, what we have is the state transition map, sometimes called STM for short. All right. So this is this map, phi over here. Okay. So we say phi is the state transition map. And what this is a map from the following spaces: T cross sigma cross U, curly U. Okay, so we're taking in an input signal, not an input value, and we're mapping back into sigma. All right, so what does this represent? What we do is we take in an end time, a start time, start state, an input signal, And what we get back is the end state. All right? So what we do is we say we start at some state sigma, we apply an input signal, from our start time to our end time, and where we end up at the end time is the output of this state transition map. Okay? So this tells us exactly how our system moves over any time period, given any initial state and any input signal. All right? So this completely describes the evolution of the state of the system. All right? So it describes evolution of state. Okay. Now let's define the readout map. All right. So just like the state transition map kind of described how the state was evolving, remember that the readout map was describing the measurement process. All right. So we denote this by R. R is the readout map. And what the readout map is it's a map from T cross sigma cross non-curly U. Okay, so we're not going from our input signal space, but we're rather going from our input value space. And we are mapping into our output value space. All right? So what we take in is we take in a current time. We take in a current state. And we take in a current input value. All right? And what is returned is the current output or measurement value. All right? So what we do is we take in the current time in our system, the current state of our system, and the current input of our system, and we return the current measurement. All right? So this was just like the function that in the shower example mapped from the time of day, the true temperature of the water, and the handle position to that value in the set that actually told us what our hand was feeling at that particular instant. Okay. So take a quick look at this definition, right? We've kind of laid out all these different objects. This was more or less everything that we kind of described in this shower case. Is this a complete definition for a dynamical system? Take a moment to think about this, okay? I'll kind of pause. Okay, so I'll assume that you thought about it a little bit. And, maybe a realization that you came to is all of these things so far are really just abstract mathematical objects, right? We haven't actually defined any structure on these things that says this needs to behave like a dynamical system, right? This needs to behave in a way that kind of respects how things evolve in the real world, all right? So if we look at the state transition map, for example, this is just some random abstract function, right? It doesn't yet obey any rules that we might expect the state transition map to, kind of respect in the real world, all right? So our next step is we need to define a couple of basic axioms that ensure this abstract definition of a dynamical system obeys a couple of basic rules, all right? So let's do this. So what we're going to do is we're going to outline some axioms. All right, so the objects above must satisfy the following. All right, so first we're going to have something called the time axiom. All right, and what the time axiom says is we could just kind of add and subtract different times in our time set without any problem. All right, so what this says is for all T1, T2 in our time set, what we have is T1 plus T2 is also in our time set, and T1 minus T2 is also in our time set. Okay? So this might kind of seem a little bit random, maybe a little bit unnecessary, right? Why are we requiring this kind of restriction? It turns out that in order to really have a watertight definition and to define concepts such as time invariance, which we'll see shortly, in a really well-posed way, this is something that we need to make sure is kind of there in our definition of a dynamical system. All right? So the basic reason for this is we'll discuss kind of how we delay signals by a certain time tau in our time set. And if we're delaying this, what we want to make sure is that if I take any time and I subtract off my delay tau, what I get back is a valid time. All right. Again, we'll talk about this more formally a little bit later. Right? Just keep this in the back of your mind for now. What else do we have? What we have is the restriction axiom. What does the restriction axiom say? The restriction axiom, says that for all times t0 less than or equal to t1, both of which belong to our time set t, all initial states, x0 and sigma, and all inputs, u1, u2, which belong to our input space. Now, I just want to remind you real quick, this is our input signal space, right? Not our input value space, right? I'm going to emphasize that these things are signals just by writing these little parentheses with a dot, okay? So if I, for example, were to substitute a u1 of t, I would be referring to the input value, all right? But since I have these empty parentheses, I'm referring to a signal. Okay, so let's get back to the restriction axiom. What does this need to satisfy? So for all inputs u1 and u2 in this set u, what I have is if u1 of t equals u2 of t for all times t in the following set, t0, t1, intersected with my time set, then what I get is that my state behavior should be the same due to those two inputs, right? As long as we're on this time interval. So t1, t0, x0, u1 equals phi of t1, t0, x0, and u2. All right? So all that this says is that if on a given time interval, two signals are identically equal to each other, they should produce the same system behavior on that time interval. All right? So let's sketch out a picture to kind of see what this means. All right? So first, I'll go ahead and plot the input signals. All right? So let's say this is our input U1. Maybe we have another input signal U2. Right? So it's kind of clear that on this time interval over here, these values of these signals kind of match up, right? So let me just make this clear. These two guys are doing the exact same thing on this time interval. All right? So what that means for the state is that if I go ahead and I plot out the state over here, what I'll see is that if this is how the state evolves due to input U1, then input U2 will need to do the same. All right? So what we have is that equivalent inputs produce equivalent behavior from time t0 to t1. All right? So it doesn't matter if my input signal values differ after this period from t0 to t1. It doesn't matter if they differ before. If these two systems start at the same point, and we apply these two input signals, which are equal to each other on t0 and t1, we should see the same exact behavior. Okay? So this is what the restriction axiom says. Now again, some of these things might seem a little bit obvious, but really in order to have a well-posed definition, these are things that we strictly require. Okay? All right. Let me just take a quick drink of water and then I'll get back to it. Okie dokie. All right. Next up, what we have is a really very fancy sounding kind of axiom. All right. And this thing is called the semigroup axiom. All right. So I'll discuss the kind of fancy rationale behind naming it this in just a sec, but for now just kind of sit tight and take this name at face value. All right? What this says is that for all times t0 less than or equal to t1 less than or equal to t2 belonging to my time set t, all initial conditions x0 in my state space and all input signals u in my input signal space, curly u, what I have is the following. I have phi of t2, t1, phi of t1, t0, x0, u. U is going to be the same thing as phi of t2, t0, x0, and u. Okay, what's this thing saying? What this effectively says is that if I first go from t0 to t1, applying an input u, and then I go from t1 to t2, applying that same input signal u, what I get is the same exact thing as going from t0 directly to t2 and applying this input u. All right? So the semigroup axiom is effectively a statement that says the state transition map behaves well under composition. All right? So if I compose the state transition map with itself, I end up with something that kind of makes sense, right? If I first go from t0 to t1, and then from t1 to t2, I should get the same thing as just going from t0 straight to t2, okay? So I mentioned I would talk about the rationale behind the name. And this comes from some connections to algebra, right? So if you're interested, you can go ahead and read about semigroups / semigroup actions, all right? So you could open up any algebra textbook or just give this a Google and just kind of see if you could notice any connections between the definition of a semigroup or a semigroup action and what we've just said over here, all right? This is, again, really just a fancy way of saying the state transition map behaves well under composition, okay? All right, so we'll finish off with one more axiom. What we have left is the identity axiom. Okay, what the identity axiom states is the really simple idea that if no time passes, nothing happens, all right? So if we go ahead and we put this in math, what this says is for all times t in our time set, all states x in our state space, and all input signals u in our input signal space, or just our input space, what we have is phi of t, t, x, u equals x, okay? So since these two times represent the end time and the start time, what we have is no time passes, all right? And since no time has passed, we should stay in the same state, okay? So this is all that the identity axiom says. All right, fantastic. So there's one remark that I want to make about this definition, all right? So just to clarify, this is the end of the definition over here, all right? I know we were writing it for a lot. It seems like it would go on forever, but we just about did it, okay? So what's my remark? Well, we said that this is something called a causal I/O dynamical system. All right, but we never really mentioned what causality actually means, all right? Now is the time where I'm going to do that. So what we say is a system is causal if its behavior only depends on its past inputs or states. Okay? So our system cannot depend on any future information. All right? So where's this idea of causality kind of showing up in our definition of a causal I/O system? Well, it turns out that the idea of causality is really baked into this restriction axiom over here. All right? So what we have in the restriction axiom is that even if signals u1 and u2 differ after time t1, right, our state transition map is completely agnostic to this, right? It doesn't care if these two input signals differ after time t1. All that it cares about on this interval from t0 to t1 is what the input signals are doing beforehand and not what they're doing in the future, okay? So even if these two input signals diverge, we should have the same behavior before that divergence. Okay, so this is the basic idea of causality. Up until the present, our behavior only depends on things in the present and things in the past, not on things in the future. Okay. So let me just run through a couple of quick exercises. All right. Let me state these. So in each of the following exercises, what you should do is you should come up with a formal. What I mean by formal is a definition, is something that matches the definition that we just laid out above. A formal causal I/O system of 1, a falling rock, right? Super groundbreaking. 2, an airplane. And 3, a computer. Okay, so take a moment, give this exercise a go. See if for each of these different systems you could kind of work out, what the state space is, what the input space is, the time sets, state transition map, all of these different things. All right. So I just want to remark real quick. In order to do this in a kind of tractable way, you'll need to make some simplifying assumptions about each of these different systems. And as long as you're upfront about what these assumptions are and you kind of understand whether they're good or bad assumptions, this is not such a bad thing. Okay? So give this a try. See if you can kind of get a feel for how these different systems fit into this formal I/O dynamical system kind of business that we just defined. Okay? All right. So now that we've kind of laid out this very general abstract definition for dynamical system, we got to kind of figure out what to do next, right? Now, ideally, what we'd like to do is just kind of jump right into it and start performing analysis, designing controllers, analyzing stability, all of this different stuff. But, we got a couple problems that we have to deal with, right? And the main problem that we have is really a general principle in mathematics, right? And that is generality comes at the price of practicality. All right, so this is a kind of universal principle. This holds for more or less everything. If you have a super general definition, right, something that really applies to a huge range of examples, then it's not really a super useful definition, right? If we haven't assumed any kind of particular structure, then there's not all that much that we could really say about our system, right? So for example, in these exercises I outlined above, we cover this really wide range of examples, right? And because we cover such a wide range, there's not so many interesting things that we could say, right? Falling rocks, airplanes, and computers are all pretty different systems, but they all fall within the same framework, right? So what's our solution? So what we have is, in order to more productively study dynamical systems, we must add more structure. All right? So you could think of this super general definition we outlined above as really kind of some general scaffolding, right? Some very basic framework for what a dynamical system is. Okay? Now what we're going to do is we're going to really build upon this basic structure and kind of flesh out some more interesting and rich examples of dynamical systems. All right? So what's the simplest kind of structure that we can add to this system up here? something really easy that we can do is we can add structure to our time set. All right? So we can request that the time set of the system satisfy some interesting properties. All right? So this is pretty easy for us to do. This leads us to the following definition. Continuous time system. All right? So a system, note that whenever I say system, I'm automatically referring to a causal I/O dynamical system, right? Just because that's a little bit of a mouthful to say, I'll just say system to keep things nice and easy, okay? So a system D is a continuous time system, which I'll abbreviate continuous time system, if its time set t is just equal to r, okay? So if t equals r, right? So this is something like the shower example, right? Here, time was passing continuously, right? We were continually taking measurements. We were moving in real time. Time was being measured in seconds, right? So something like the airplane or the falling rock might kind of fall into this category of systems as well. All right, so what else we got? So we have a continuous time system. What we also have is a discrete time system, right? So definition of a discrete time, let me add a little dash here, time system. And a system D, let me just write a couple dashes, is a discrete time system if, instead of being a real number, our time set t is now going to be the integers, all right? So if t equals z, all right? So instead of time passing continuously with a real number, time will jump at discrete increments, all right? So if we use something like a very simple model of a computer, this might be an example of a discrete time system, right? So what happens is computers, or at least simple models thereof, kind of jump at discrete intervals in time, right? They don't make decisions continuously. All right. So what other structure might we want to add? What other structure might we add? Well, so far we've been talking about structure to do with time, right? Let's kind of continue this sort of time theme for a little while. Let's consider the falling rock, all right? The falling rock. Let's see if we could kind of pick out any structure that we haven't already lined out that this falling rock system satisfies. Okay, so let's say suppose we drop the rock at time t equals 0, okay? And we go ahead and we record its trajectory. If instead we wait around for 10 minutes and drop it at time 10, what will happen? Will the trajectory of our rock be the same? Kind of most likely, right? What we have is that the trajectory of the rock will be the same, okay? So there's kind of some basic idea going on here that the behavior of our rock is not something that depends on the objective time in our universe, right? The number of seconds since the beginning of time really don't determine how the rock will behave, right? It's only the number of seconds since we dropped it that are actually making the difference here, okay? So this difference between seconds, I'll say, since beginning of time, or beginning of the universe, versus seconds since, I'll say, the beginning of our experiment, in which we just kind of drop the rock and then start recording time afterwards, is encoded in the concept of time invariance. All right? So what we say is systems that kind of exhibit this property in which it's not the number of seconds since the beginning of the universe that matter, but rather just the amount of time that has passed since we started our experiment that matter. These systems are said to be time invariant. All right? So this is still a rather hand-wavy concept, right? We haven't actually put any mathematics down to it. So what we'll do is we'll spend the next couple of minutes really just formulating a nice, precise definition for time invariance. Okay? So there's actually a couple of different things that we need to do before we can actually go ahead and put down a proper definition for time invariance, right? We have a little bit of bookkeeping to do. So what I'll do is I'll make a couple of auxiliary definitions, and then I'll work my way back to coming up with a formal definition of time invariance. All right? So the definition of time invariance that we'll present in this course is something that only depends on the inputs and outputs of the system. All right? So what I could do, right, is I could go ahead and I could say, okay, I'm going to compose my readout map with my state transition map, and I'm going to describe everything in terms of that composition. But I don't really want to keep rewriting that composition all the time, right? That notation becomes a little bit cumbersome. So what I'll do to avoid this problem is I'll just make a definition, okay? I'll define myself out of this hole like any good mathematician. All right. So I'm going to make a quick definition. And this is just one that just reduces notational overhead, all right? There's not much more to it than that. This definition is called the I/O map. Okay. So what I have is, given a system, right, a causal I/O dynamical system, D, the I/O map is defined rho, which goes from T cross sigma cross U, right? So this is the same domain as my state transition map. And what it maps into, instead of mapping into sigma, it maps into my output value space, okay? So this maps into the space Y. And how it's defined is just as the composition of the readout map with the state transition map, okay? So I have rho of T1, T0, X0, and U is equal to R of T1, phi of T1, T0, X0, and U, then my input at time T1. Okay, so as you can see, the I/O map just gives us a direct path from input and initial state and our times directly to our output value, all right? This way, we just don't have to keep writing this composition every time we're kind of interested in reading off this output value at a given time. Okay. Remember, just to reduce notational overhead, okay? Nothing too fundamental about this. All right, so let's get back towards our goal of defining time invariance for a system. So if we want to define a system to be time invariant, a nice first step might be defining a couple of individual pieces of this system to be time invariant, right? Remember that this formal dynamical system, it involves a lot of different objects, right? The actual dynamics of the system are really not the only things that are there. So to make sure these systems are time invariant, we need to make sure all of these different objects are time invariant in some sense. Okay, with this in mind, what we're going to do is we're going to start off by defining some notion of time invariance for the different sets in this system. Okay, so let's define a delay invariant set, all right? So inv stands for invariant in this context. So what I'll say is consider a set of signals. This set is going to be, I'll just call it curly U. It's not necessarily the input space to any system. I'm just using curly U for the sake of convenience, right? So curly U, subset of the set of all functions from time t into some fixed set U, where t is a time set. All right? So if for all tau in my time set t and all inputs u in this set u, if I have that the signal u hat of t, which is defined u of t minus tau, satisfies the following property, u hat still belongs to u, then I say u is delay invariant with respect to the time, the time set t, okay? So basically what's happening here is if I can take any input signal in this set over here, any signal in this set, and I delay that signal by any time I want in my time set, and that delayed signal still belongs to this set u, then we say u is a delay invariant set, okay? So I take any signal, I delay it. If that signal still belongs to my set, this set is delay invariant, all right? So right here we've said delay invariant with respect to this set t. When the set t is clear, we could just say it's delay invariant, all right? Okay, let's continue. So far we've defined this delay invariant set, right? And this set we defined on kind of this path towards getting a clear mathematical definition for time invariant systems, all right? Let's now take one more step towards that. All right, next up, I'll define something called the delay map, all right? So what I'll say is consider a delay invariant set u, okay? So for a time tau in my time set t, the delay map of time tau is the map t sub tau, which maps from my input signal space u back into my input signal space u, and it's defined such that t sub tau of any signal u evaluated at time t is equal to u evaluated at time t minus tau. Okay. So what this delay map does is it takes any input signal, or just any signal rather, in this delay invariant set, and it just delays it by a time tau. Okay? So what I want to emphasize real quick here is I just take in an input, or I take in any signal in this set u, I just shift it back by an amount tau, and what I get is the result of applying this delay map, okay? So just as a quick side note, I want to highlight something real quick. If tau is less than 0, this delay actually shifts the signal forward. Okay. So just make sure, because of this little subtlety over here, make sure that you kind of reconcile your intuitive definition, kind of in your mind of what the word delay means with what it means in this context, right? If we take a negative time, what we're doing is we're not really intuitively delaying a signal, we're actually shifting it forwards, all right? Okay, so now that we have the idea of a delay map and a delay invariant set, we can provide a really precise definition for a time invariant system. Let's do that. So definition, a time invariant system. Okay, so we say that a causal I/O system, D, is time invariant if the following properties are satisfied. So remember, we said earlier, the dynamics of this system are not the only thing that should be time invariant, right? The different kind of objects, the spaces of this system also need to satisfy some sort of time invariance property, all right? What this means is that the first condition of time invariance will be that the set U, the input space of this system, should be a delay invariant set, okay? So the input space U is delay invariant. Now we also require that the output space should be delay invariant. So 2, y is delay invariant. Now we just require a one remaining condition on the dynamics. All right. What we say is for all times t0 less than or equal to t1 belonging to our time set t, for all times tau in our time set t, which represents a delay, for all initial conditions x0 in our set sigma, and all input signals u in our input space u, what we have is our output rho at t1, t0, x0, and u is equal to our output rho, which is delayed. Okay, so t1 plus tau, t1, t0 plus tau, x0, and the delayed input signal, t sub tau of u. All right. So what this effectively says is that if we shift all of our data by a time tau, we should kind of get the same output behavior. All right. Okay. Fantastic. So let's get a quick intuitive idea for what this sort of behavior looks like. All right. Let's sketch out an example of a time invariant system. So first, let me go ahead and plot an input signal on this set of axes and plot a delayed input signal over here. So what I'm going to do is I'm going to say my original input signal, maybe it jumps up at this value t equals 0 over here. Okay, this is u. And what this does is it produces the system response of a ramp starting at time t equals 0. Okay, so I have something like that, and then my system does that. All right, so that's rho. Now, if this system is time invariant, then what will happen if I take my input signal and I just shift it over by a fixed time tau? Right, so this is t sub tau u. This is time tau. Okay. So as you can see, all that we've done is we've just delayed the appearance of our input signal u, shifted it over by a time tau. Well, what will happen is if the system is time invariant, the corresponding output should just be shifted over by time tau as well, right? So what we'll see is that the output should satisfy this, right? So all that's happened is we've delayed our input, and we see that our output gets delayed as a result. Okay, it's the same exact signal, just pushed all the way on over to have the same delay as our input signal. Okay, so this is time invariance.